Hey, welcome to the Explainer. So today we're going to talk about the invisible rules that literally stop our digital world from falling into total chaos. Seriously. It's this hidden dance happening inside your phone, your laptop, right now. And we're going to pull back the curtain and see how it all works. All right, let's just jump right in with a super simple example. Imagine you and a friend have a shared bank account, and it's got $100 in it. Now, at the exact same time, you both check the balance. You see 100 and you decide to deposit 50. Your friend sees 100 and they decide to deposit 20. So you go ahead and write the new balance, 150. But a millisecond later, your friend, who also started from that same $100 balance, writes down their new total, 120. What's the final balance? It's wrong. Your $50 deposit just poof, vanished, because your friend's update overwrote yours. Now, what's really wild is that this exact same problem happens inside your computer millions of times a second. Don't worry about trying to read all the code here. That's not the point. The point is what it shows. Instead of people, you've got processes. So one process reads a value, but right before it can save its new calculation, the computer does something called a context switch and jumps over to another process. That second process reads the old value, does its own thing, and saves it. Then, when the first process finally gets its turn to save, it just stomps all over the second one's work. The result? Corrupted data. Chaos. This whole mess, this uncontrolled free-for-all where processes are just tripping over each other, well, it has a name. And it's the absolute fundamental problem that computer scientists had to solve to make any of our modern gadgets work at all. It's called a race condition. And it's pretty much what it sounds like, right? You've got multiple processes literally racing to mess with the same piece of shared data. And the final result? It's just a matter of luck. It completely depends on the random order they happen to finish in. It is a perfect recipe for disaster. So to prevent these races, to bring some order to that chaos, a really clear set of rules was established. You can think of them as the rules of engagement. Any correct solution, absolutely any of them, has to follow these rules. No exceptions. First things first, you have to identify the danger zone. This is that specific little chunk of code where a process actually touches the shared data. Like that bank balance. And we call this the critical section. Honestly, the entire problem just boils down to one goal. Make sure that only one process is ever running inside its critical section at any one time. And that goal leads us to these 3 sacred rules. Number 1, mutual exclusion. Super simple. If I'm in the critical section, nobody else gets in. It's a one-at-a-time club. Number 2, progress. If the club is empty and I want to get in, you, who are just minding your own business outside, you can't stop me. And number 3, bounded waiting. You can't just be stuck in line forever. Everyone eventually has to get their turn. Okay, so with those rules in mind, let's go on the quest to find an actual algorithm that can follow them. The first few attempts were pretty clever, you have to admit, but, well, they all had a fatal flaw. So the first idea seems obvious, right? Let's just have the processes take turns. You go, then I go, you go, I go. Simple. But here's the problem. It violates that progress rule. What if it's your turn, but you're off doing something else that takes forever? Or maybe your process just crashes completely. Well, now I'm stuck. I'm just sitting here waiting for a turn that is never going to come, even though the thing I need is totally free and available. Not good? And you can see the problem right here in the code. You don't even have to be a programmer. See that line that says, while turn, not I? That's something we call busy waiting. The poor process is literally just sitting there, burning up CPU power, asking, is it my turn yet? Is it my turn yet? How about now? It's so inefficient, and it grinds to a complete halt if the other process gets held up. All right, so attempt number 2 used flags. The idea was a process raises a flag and says, hey, I'm interested in going in. Then it checks to see if the other process's flag is up. But you can probably guess the flaw here. What if both processes raise their flags at almost the exact same instant? Well, they each see the other's flag is up, and they both politely decide to wait. And now you have a deadlock. It's a digital standoff where they'll just wait for each other forever. So this is the crucial point, right? Taking turns didn't work, using flags didn't work. On their own, they were both flawed. But what if you combined them? What if you could take the best parts of both ideas and use them to cancel out the weaknesses? And that brings us to Peterson's solution. It is an incredibly elegant algorithm that does exactly that. It's genius, really. It uses flags to show I'm interested, but it also uses a turn variable to break any ties. It's the combination that works. It successfully meets all 3 of our rules, mutual exclusion, progress, and bounded waiting, and it finally solves the problem, but only for 2 processes. Yeah, that's the big catch. It's great for two, but our computers are juggling hundreds of processes at once. Peterson's solution just doesn't scale. I mean, can you imagine trying to manage that complicated web of flags and turns for hundreds of different things? It would be an absolute nightmare. We need a different way to think about this for a lot of processes. So for that, we have the bakery algorithm. And honestly, it works exactly like the take a number machine at a deli counter. When a process wants to get into the critical section, it just takes a number that's higher than anyone else's. And then the system just serves the process holding the lowest number. It's a really simple, really fair way to manage this for any number of processes. Okay, so these algorithms are amazing, and they are the theoretical foundation for all of this stuff. But let's be real, modern programmers aren't sitting around writing the bakery algorithm from scratch every day. We've built much simpler, more powerful tools on top of these core ideas. And the source material really hits the nail on the head here. It says these solutions are just too complicated and inaccessible to application programmers. It's true. So, to make everyone's life easier, operating systems give us these higher-level tools that just handle all that messy complexity for us. The most common tool by far is called a mutex lock. The best way to think about it is like a key to a single bathroom. Before you go into that critical section, you have to acquire the lock or get the key. And while you have it, nobody else can get in. When you're done, you release the lock and put the key back for the next person in line. And what this means is that for the programmer, the logic becomes just beautifully simple. You just write, acquire lock, do your critical work, release lock. That's it. All that complicated stuff about fairness and waiting and taking turns, it's all handled for you behind the scenes. Now, for things that are a little more complex, we have semaphores. So if a mutex is like having one key for one room, a semaphore is like a front desk that has, say, 5 keys for 5 identical rooms. It lets a specific number of processes, in this case 5, access a resource at the same time, but no more than that. It's a really powerful way to manage a whole pool of resources. So, we've gone on this whole journey, from absolute chaos to these complex algorithms to these much simpler tools we use today. But why does any of this matter? Why should you care about this invisible dance happening deep inside your computer? Well, because it is the absolute bedrock of modern computing. Without this stuff, without these rules, pretty much nothing in our digital lives would work. Every tab you have open in your browser, every single database transaction, every core in your phone's processor, every server running in the cloud, the entire global banking system, it all depends on these principles to keep data from turning into complete and utter nonsense. So what this explainer shows is how we have painstakingly created order out of this constant threat of digital chaos. But it does leave us with one last question to chew on. Our entire fragile digital world is built on this core assumption that all these processes will politely cooperate and wait their turn. So what happens when one of them decides not to?